Last class we discussed short circuit protection for the voltage regulator, and we saw a crude way of doing some short circuit protection, wherein we sense the current through the load using a resistance R sense and made use of this voltage across the R sense to divert the drive into the pass transistor. This is the method of short circuit protection adopted in most of the power ICs. Okay. Whether it is the voltage regulator IC transistor or power IC transistor, whatever it be. Okay. This is the method, common method of short circuit protection adopted universally in all integrated circuits. Once again, the drive otherwise would have increased the current through the power transistor is diverted onto another transistor which is getting proper biasing because of the current increase. Now, that kind of short circuit protection results in the voltage source being converted into a current source thereafter, and therefore, the current is going to remain constant. We found that the power dissipation under that situation in the IC is lowest at this point, but highest at this point. So, gradually increasing from this point to this point, and nobody can guarantee us as to what exactly is going to be our short circuit situation, and therefore, this kind of situation is not a good thing for the IC. Therefore, we would like to immediately sense the load and find out that the load is in excess of what is correct, and thereafter we want to have our own dissipation in the IC which is as low as possible, okay, until somebody comes and rectifies the error. So, we have to sense both current as well as voltage for that purpose, because we should know what is the voltage and what current I should sustain in order to sustain that voltage, okay, which can be anywhere between this and this. Okay. So, in such a situation, that particular protection scheme is going to result in what is called a fold back short circuit protection scheme. What it is we will see, but this is what we want. So, the characteristic of the voltage regulator will be having a knee at this point, which we will call as I knee, which is the same as the earlier short circuit current, and we will have this as what is called as I hold. So, these are the 2 points between which we have to have a line. That means, this is again a line, straight line with V naught as y axis and I naught as x axis. So, it will be just an equation of a line. We have to obtain this kind of line using the hardware there. So, how do we do this? Let us now therefore discuss this scheme. We will remove the old scheme. So, the same transistor is now going to be used to divert, that is, that basis of diversion of excess current drive into the series pass transistor is still followed, but the method adopted is now different. Okay. How do we do it? We know that if this is V naught, the voltage at this point is going to be V naught plus I naught RS, if you ignore the current in this, right. Voltage at this point is going to be both dependent upon output voltage and output current, but this might be a huge value of voltage, whereas we require only about 0.7 volts to be derived out of this. So, obviously, this has to be attenuated. That is one way of getting another variable. You have to have 2 points to be located in a line. That means, you have to have 2 independent variables, okay, to fix up the equation. So, I now generate from this a voltage which is going to be low enough. So, let us say we will put here another attenuator which we will call as RA and RB, and take portion of that voltage. Okay. What will be that voltage at this point now? This voltage is going to be this into V naught plus I naught RSC into RA by RA plus RB, okay, which we will be now calling it as what? Let us say we will call it a single variable alpha. Yeah, RA and RB should be large. Just as we select R1 and R2, we are also going to be taking care not to take away too much of current from the load. Okay. So, alpha is nothing but RA by RA plus RB. That is a small enough voltage which we can use, and then that voltage has to be, okay, that is, I am sorry, that voltage has to be used to bias the transistor, okay, in such a manner that the 0.7 volts is still got now. Okay. So, you can see the connection now. This voltage minus what? V naught, the other end is connected to V naught. So, it is now made very small by having an attenuator as well as subtracting a huge voltage from it. Okay. That should be made equal to what? V gamma, that is nothing but VBE. So, please once again see RA by RA plus RB of V naught into I naught RSA is the voltage here, which is alpha times V naught plus I naught RSC minus V naught. If you make alpha equal to 1, just let us see, it will be our old scheme, right. Just see, this will be connected to this will be automatically connected to that. Only thing that we have now done is we have sensed a voltage, okay, which is dependent upon the output voltage as well as output current, okay, by introducing an attenuator. So, what is this going to be now? This is nothing but V gamma equals V naught, okay, into what? Alpha minus 1 plus I naught RSC alpha. Okay. Once again you can check this, okay. When V naught is 0, we still must have a voltage which is equal to V gamma to sustain this in whatever position it wants. That is why it is called the hold current. Okay. This is the point where V naught is 0. That even when V naught is 0, I naught, the other variable, should be able to still hold the transistor which is diverting the current in operation. That is why that current is called the hold current. Now, this is nothing but the equation of that line. Okay. You can see that at one point, what is it? V naught equals V reference into 1 plus R2 over R1. We know the value of I naught. What is it? I naught is going to be I knee, whatever be the maximum current that you are letting through this system, right. That is earlier called the short circuit current, that is the knee current. That is one known point. This voltage is known, this current is known. Okay. The other point is V naught equal to 0, I naught is equal to what? I hold. I hole, what would you like to have it as? 0. But we know it cannot be 0 simply because we have to hold, right. That is why the need for I hold to be non-zero. But then I would like to have it as small as possible. The question is, can you make it very, very small? What is it that is going to cause problems? One thing that you have to see is alpha has to be less than 1. In solving this equation, you must have alpha less than 1. Okay? So, actually when I naught is 0, it should intersect at the negative value, which is magnitude of V naught into 1 minus alpha, right. That is that point. So, now my problem is, let us take a typical example. Let us say V reference into 1 plus R2 over R1 is 10 volts. I am giving you an idea as to what are the limitations that will come in practice, because unless I give you a problem here, you will not able to appreciate this 10 volts. Then we will take I knee as, let us say, 0.5 amperes. So, I knee is known as 0.5 amperes. Let us have I hole equal to, let us say, I will just take it as 0.2 ampere. I am just not sure whether this is the right value or not. Let us see what the trouble is going to be. Can you now find out the alpha and RSE? These are the two unknowns in this equation, right. I have given you all the points here. So, please find out the value of alpha and RSE. So, quickly do that, then we will know what the trouble is regarding this. So, V gamma is 0.7, let us take. V naught is going to be equal to 10 volts, alpha minus 1, plus I naught is 0.5 amperes, RSE alpha, and therefore, then V naught is equal to 0, again 0.7 equals I naught is I hold, which is 0.2 amperes, and then RSE. So, from this you will get RSE into alpha as how much? RSE into alpha equals 3.5 ohms. Is it understood? So, you know RSE into alpha as 3.5 ohms. So, 0.7 equals 10 into alpha minus 1 plus 3.5 into 0.5. So, what is the value of alpha? 0.895. 895. Already it is coming close to 1. Obviously, if I had taken it as 0.1, if I had taken what? The I hold current as 0.1, this would have increased to 7 ohms, this would have increased to 7 ohms, and you would have had problems with the alpha, right? Okay, alpha has to be less than 1 and positive. Okay. So, you cannot make alpha, okay, smaller than a certain value. Okay, this is one thing that limits alpha. That means I will take that alpha which is going to be such that this particular current is as small as possible. Even that may be a dangerous thing. Why? Already we have seen that suppose I have this kind of short circuit protection at 0.5 amperes. So, let us say I want RSC equal to 0.7 divided by 0.5. If I want this kind of short circuit protection, the RSC is going to be 0.7 by 0.5, which is how much? 1.4. Okay. If you are adopting this kind of situation, RSC is going to be 1.4. Whereas, suppose I say that is not good, that is not a very efficient way. I am going to have 0.5 as the knee current and 0.2 as the whole current. Then this scheme gives R sense as how much? No, R sense we have already evaluated 4 ohms, is it? So, it is greater than what we have earlier had. Okay? Okay. What does it matter? It matters a lot. Okay? We are talking of currents of the order of 0.5 flowing through now not only the pass transistor, but also the series resistance, which is this. Okay? And therefore, this will add as an additional drop between Vi and Vout. Let us now just see what is the drop in this situation. In this situation, it is 4 into 0.5. 2 volts drop is already here when it is working satisfactorily, right. So, 2 volts drop here and then 0.7 and then 0.7. That means V0 requirement, Vi minus V0 requirement, that differential requirement is increasing. Okay. This is how things are going to result in. If you therefore try to go for smaller and smaller whole current, which is going to be only an eventuality when a short circuit occurs, which is also supposed to be quite rare phenomena, right. Then there is no point in losing when it is in operation, okay, its functionality for a large variation in input voltage. This is something that normally is ignored in the laboratory, right. They try to make the I hold as small as possible and get a RSC of the order of few ohms, and then see that it is not working as a regulator simply because they have retained the input voltage at the same value. Now, the input minimum required is going to be higher than before. Okay. So, this is a common error in the laboratory that occurs while testing out this fold back short circuit protection invariably, because in your enthusiasm to make I hold very small, you will come up with RSC which is going to be very large, wherein large amount of voltage, series voltage drop is going to occur and requiring a Vi minimum which is going to be very high. Okay.
The load regulation also will
yeah, apart from this, the output impedance, as he points out, is invariably going to have, again these are all things which are going to be spoiled for our normal functioning, just in order to take care of, okay, a short circuit protection. The output impedance is going to be always, okay, without feedback, is going to be involving RSC, okay, straight away. Now, what happens in the output impedance normally is, just look at it, because since he has pointed it out, I would like RSC plus Re of this transistor. But if the transistor is operating at high current, that small Re is going to be negligible. So, RSC is what is going to fix up the basic output resistance without feedback, and then the output impedance of this current source, that divided by beta. So, the output impedance without feedback is going to be fixed only by primarily by the output impedance here divided by beta rather than any of these resistors. Okay? Is this clear? Even when this is pretty high, this is not going to fix up the output impedance, okay, because we are going to make this particular thing very high, that divided by beta is the output impedance without feedback. With feedback, it is going to be reduced by the loop gain of this stage anyway. So, that output impedance is going to be low because of the fact that there is negative feedback here. So, when you evaluate output impedance without feedback, please note that even though this comes into picture, okay, this point is at a high impedance point, and that divided by beta is the one that normally, okay, fixes up the output impedance without feedback. Is that clear?
Sir, can't we make alpha greater than 1 by putting an amplifier there?
Yeah, but we would like to have this as a passive structure. Any amplifier, any protection circuit, you have to make it purely passive, as much of it as possible, right. Obviously, this is the only part, okay, which is active here, rest of the things are all passive. That is the reason. It is like negative feedback being used for improving the performance or desensitizing the performance factors from the active parameter. So, we do not want our protection circuitry, okay, to depend upon any active parameter. Okay. So, now we will be just considering the fact that these regulators, when they are designed, most of the problems that we are facing will have to do with protection, power dissipation, etc. Now, if we are trying to protect the transistors or the IC, we are having problem with increased power dissipation. That is what we saw here, right. Now, why does the power dissipation occur here? That is mainly because this is a control circuit where the pass transistor is working in the active region. Okay. The technique of maintaining output voltage across a load constant involved in something like putting an active resistance, which is nothing but the transistor, and varying the drop across this, okay, in the active region. Therefore, output voltage remained constant when input voltage was varying. Obviously, if input voltage is varying by a very large extent, okay, then we have serious problem about power dissipation in the IC increasing, particularly when Vi is reaching Vi max. Okay. So, this cannot be avoided in this. So, this series regulator is not efficient scheme. Obviously, we must not use this when we are dealing with limited power, particularly in satellite applications and all, where the power is limited and we would like to conserve space also. Okay. The size should be small and power is limited, and we have to have energy efficient circuit systems there. So, most of the regulators which came up particularly for satellite applications were what are called as switching regulators. Of course, we have now seen that even television receivers and others, right, now make use of this, okay, because it is very small in size for the same, not only that, very efficient in spite of large variation, particularly in a country like ours where the input voltage variation is a very small, very large. Okay. We need such regulators, okay, to make the circuit still remain functional. Now, what is the basic principle under this? I am illustrating this basic principle here as an application of this IC regulator only to bring out the fact that later on we will use the same principle in a variety of places like class D power amplifiers and multipliers. Okay. So, the idea behind this control scheme is very important, okay, and that is what we are going to illustrate by taking regulator as an example. Okay. So, let us understand something about what are called converters. Once again, in power business, these converters are now available in a variety of packages, okay, for you, and these are very useful components like regulator ICs. Okay. These are also other IC components which are universally used in a variety of applications, particularly power applications. Converter. What is a converter here? I want to convert a voltage, let us say Vi, into another DC voltage in a very efficient manner. What does it mean? Efficiency should be 100%. How to convert a DC into another DC? So, what is done here is use a switch, okay, and then charge a capacitor. So, capacitor can store energy for us. Okay. So, use a switch to charge a capacitor, and then when the input voltage is removed, okay, we must still have some means of, okay, keeping the capacitor charged. Okay. So, this is something that is not done very efficiently by any scheme other than another energy storing. So, basically now we would like to, let us say, have a voltage here which is being switched from Vi to 0, let us say. Okay. So, Vi to 0 in a complementary fashion. Okay. So, what happens? Vi for tau and 0 for rest of the time. No, capacitor means I am not changing the voltage, I am just charging it and going to use the same voltage, okay, for further application. Now, I would like to charge and discharge, okay, so that the voltage average resulting out of this is how much? It is charge to Vi and discharge to 0 immediately, charge to Vi, discharge to 0. Okay. So, Vi into tau by T. This is the DC component of this. So, this is a very efficient converter so far, right. But how to obtain the average? Waveform obtained here is this. Do you understand this? That is all. Waveform is still having all sorts of ripples, right. So, we have to get rid of the ripples. How do you do it? You have to put a very efficient low pass filter. So, what is a low pass filter? Put a series inductor and a capacitor. This is an efficient low pass filter. I can also build a filter using a R and a C, but again R is a dissipative element. So, I do not want to use any dissipative element. Now, you see that this is the most efficient DC to DC converter one can think of. Okay. I have put only one LC filter block. If I put more number, the filtering is going to be better, right. So, but for illustration we will go to the simplest converter available, and here the voltage is going to be Vi tau by T, and you can draw your current I naught from this. That means we have to have two switches and switches are again ideal elements having 0 power dissipation. These switches are going to be active switches, in the sense they are going to be MOSFETs or transistors. Okay. Inductor, ideal inductor, 0 dissipation, ideal capacitor, 0 dissipation. Right. The places where dissipations occur, you have to again keep note of, so as to see how far it is going to be close to 100% efficiency. In this case, obviously input power is going to be, what is it, Vi, okay, into II average. Actually output power is going to be V naught into I naught average, right. Okay. Now input power is going to be Vi into II, okay, and it is conducting only for tau. So this is nothing but the output power. So efficiency is 100%. Okay, I average, okay, is same as I naught average. Is this clear? No. Efficiency is equal to 100%. The cause for the efficiency to deviate from 100% is going to be the fact that switches are going to dissipate certain amount of power, because they are going to be transistor switches. And once again we have discussed it maybe earlier. Remember, in the case of digital scheme, I had discussed it thoroughly. When this diode or transistor is on, the power dissipated is VCE sat into I naught, whatever current that is flowing through it. Okay. And when it is off, whatever voltage is coming across it into the leakage current, which is going to be very small normally. Okay. So these switches also dissipate power. There is going to be some DC resistance or AC resistance here, which is going to cause certain amount of power dissipation. There is going to be here a leakage resistance, which is also responsible for certain amount of power dissipation. The primary power dissipation occurs in switched power regulators in the switches when they are on, and the inductor because of the finite resistance. Okay. Rest of the power dissipations are negligibly, components are small. Now how do we analyze this? Analysis of this is one of the most exciting piece of engineering approximation, because this analysis, if it is done, how can you do it? There are a variety of methods of doing it. Okay. You can use your Laplace transform, you can replace this waveform by its transform equivalent and replace the entire thing by the corresponding transform. After this, you know the waveform applied, okay, and obtain the output. That is going to be good job for networks. Okay. Or you can find out the Fourier components of this, and for each component you can find out the output component, since you know the L, C and R component in this. But we are not interested in such a thing. We are interested in designing a good converter, efficient converter. What it means is the ripple voltage here is assumed to be extremely small. Already you are assuming that L and C have been chosen in such a manner that V naught is for all practical purposes equivalent to a DC. Okay. So let us therefore use this information in coming up with the solution for this. Let me start. This is Vi for tau and this is T. What is the voltage across the inductor? It is going to be Vi when this is open, okay, 0 when it is closed. So, when it is open, this is V I, and what is the voltage here? At all times it is V equal to V naught. I am going to consider that is not correct, that is an approximation, okay, but that is good enough. So, this is V naught and this is V I. So, the voltage across the inductor when it is connected to the supply is V I minus V naught. So, what is the current through it? V I minus V naught by L into T. A DC voltage is applied across the inductor of magnitude V I minus V naught. So, the current in the inductor is going to be 1 over L integral V dt, right. V is constant, V I minus V naught. So, this is going to be V I minus V naught by L into T. It is increasing linearly. Once again, this is an approximation. I have already assumed steady state solution, okay. That is why I am assuming V naught to be already a DC. That means, when it is off, what will be the voltage? V I is 0, V naught is remaining V naught. So, it is minus V naught by L into T. What does it mean? The voltage is, the current is decreasing. The increase in current must be the same as the decrease in current, because after all again it is going to start, this is the steady state waveform, right. So, that means delta I L is going to be V I minus V naught by L into tau, correct, that is the increase within a time tau. So, that is going to be equal to, okay, V naught by L into T minus tau. This is not a new relationship, this is nothing but again V I tau by T relationship. If you remove the L, right, you will see that you will get the relationship which is V naught equal to V I tau by T. This is also going to result in the same relationship V naught equal to V I tau by T. But what it tells us is what is the extent of current variation that is occurring in the inductor. Is that clear? Now, that is important because I must design the inductor also.
The other current is negative only.
The current is, let us see, please understand this, current is I naught. Where is this I naught flowing? Through this. This DC current cannot flow through the capacitor, okay. So, there is an average current in this which is I naught, okay. Around the average current, the current is increasing above it by certain amount and decreasing. So, that is the idea of negative current, okay. It is not negative, current is flowing only in one direction through this, okay. So, current is always flowing this way, right. What happens is it is going to be delivering both the load current and the capacitive current when it is connected to input, and only the load current when it is connected to the input, not connected to the input, okay. So, this is important, this change in current. Normally in a good design, by if you want the ripple at the output to be small, delta IL itself should be small. This is the change in current which will be flowing through a combination of resistor and capacitor. If this itself is made small, okay, the ripple will be smaller. So, how do you make ripple small? By making L large. L cannot be made too large because the size of the switched mode regulator itself will increase, okay. So, typical value of delta IL accepted in a normal design is about 10 to 20% of I naught, okay. I naught is the average current for which you are designing. Let us say take a problem like 5 volts converter you would like to design for delivering a current of 1 ampere. So, that means delta IL we will fix it at something like 0.2 amperes in order to keep L in a limited manner, right. So, this current is going to be flowing into what? Let us again see, this is how engineers must do approximations and arrive at sensible ideas in design. This current is comprising both the DC current and the change in current. The DC current will flow into the resistor, now you have to assume obviously, right, and AC current, that change in current, will flow entirely, if you have done a good design, into the capacitor, right, and develop a voltage dependent upon what the current is. How do you find out the voltage across the capacitor? You know the current waveform, triangular. So, what is the waveform of voltage across the capacitor? What is the value of voltage? How do you find out? Integral I dt, you know the current. What is integral I dt pictorially? No, no. What is the operation integral I dt? Area under the curve. So, that is it, right, this area. So, what is that area, can you tell me? What is the width of this triangle? Quickly, it is a periodic waveform, T by 2, right. So, the width of the waveform is T by 2 into height delta IL by 2, half of it is the area, okay, 1 over C. You understand the mathematics of it is very simple. What is this voltage? This is the voltage, okay. This is the way voltage is going to increase and decrease. Voltage is going to increase up to this, it becomes maximum at this point and then decrease. So, this voltage is nothing but peak to peak ripple, right. So, this is something that so we have very simply obtained, okay. Is this clear? Delta IL we already know in terms of Vi minus V naught by L into tau, okay. So, you know that T is 1 over what? Frequency, yeah, frequency with which this switch is getting switched, okay, on and off. So, tau over T is nothing but what is called as the duty cycle, okay. So, this is a very good approximation, okay. Why do I say approximation? Because strictly speaking this is not triangular, this, okay, because I have assumed output voltage to be constant. But now I am proving that output voltage has a ripple of a very small extent, right. So, this peak to peak ripple you will make it very small purposely by using this value of the capacitor here, okay. And if you do that and select the L properly, right, then all your analysis is perfectly valid, okay. And this analysis is not valid for a general case, okay, of a network problem, and that is pretty complicated. We need not know even how to solve this, okay. So, for switched mode regulator, this is the kind of analysis that we are going to adopt in evaluating the value of L, C, okay, given the specification. What is it? V naught, I naught, this is only a converter design, DC to DC converter. We have not yet come to the stage of designing switched mode regulator. Voltage is DC is converted to another DC in a most efficient manner. Now, what should I do in order to regulate? It is obvious that I can now control tau over t. As Vi changes, I will change tau over t, okay, in such a manner that Vi into tau over t remains a constant. Okay. And this idea of voltage regulator is very important, because you are multiplying this now. This is going to be done by another control voltage or something. So, this is another idea for some multiplier, okay, very efficient multiplier. So, we will see, okay, in the next class how further we can convert this whole thing into an efficient voltage regulator.